to give the Colloquium. Philip got his bachelor degree from Seoul National University in 1990, and then he received his PhD actually from applied physics in Harvard. And then he did a postdoc at the University of California, Berkeley, as a Miller Fellow. And then after that, he joined University of Columbia in the physics department. And I guess we have been neighbors for a long time. And in 2014, he decided to move to Harvard University, and he joined the Faculty of Physics and Applied Physics there. So he's a leading scientist, world-leading scientist, and famously known for his graphene work from the beginning. That was exactly when I was starting my graduate studies, actually, at Princeton, to sort of know about these ideas of having a graphite at the tip of an AFM and scratch it to sort of leave like one graphene, and then later the exfoliation. He's an experimental condensed matter physicist who has actually touched on a lot of subjects from transport, heat transport, thermal conductivity. Apart from graphene, there are lots of work, nice work actually on carbon nanotubes, organic, inorganic nanowires, and other two-dimensional materials. Obviously, he's a recipient of many awards and prizes, including the Buckley Prize. And today he's going to tell us about the Exciton Superfluid and Ferromagnetic Superconductors in his favorite material, graphene. Yeah,
thank you.
Please.
Yes, thanks, Jafar. Well, thank you very much for coming, and thank you very much inviting me over again the MIU. That I think I just looked through my old files, and I see that I think the first talk that I gave in MIU was 2004, 2005. I think that was a really beginning part of 2006. Being part of the graphene research, and that we had kind of the first report about the quantum Hall effect appears in graphene, half-integer quantum Hall effect appears in graphene. And then I was invited back again, I believe 2014, so 9 years afterward or something. And then I was talking about the Hope Shadow's butterfly again in the graphene. And then I was invited again, 2019. So I think I feel like that 8 years and 4 years, I think that period becomes shorter and shorter. I think this is kind of something I found.
It depends on your work.
And yet I'm going to talk about the graphene. But you see that there are kind of some of the many words here that I will try to explain that what these are about. But again, the main platform that I'm talking about is this guy, graphene. So, as Javad mentioned, experimental discovery of the graphene was happening in 2004. That was kind of accidental discovery in some sense. You're just using scratch tapes and take it out. That the single atomic sheets, and immediately that was recognized that there is interesting physics going on. Effective Hamiltonian that describe electron dynamics in this system resemble the Dirac Hamiltonians, and that probably give us that quite different type of the electron dynamics one can imagine. And this, in a sense, tied with also all this topological insulator type of the discussions there. And that was actually a good starting point. But in some sense, if you just look at the graphene, this is a relatively simple material. So there is only one element, carbon, right? And the band structure, although there is some interesting tweaks related with the Dirac equations, but nevertheless, band structure is also very simple. Typically, electron or density of state that fill up this Fermi level is relatively small. So the physics here, that most of physics you can understand, just using the single particle type of physics, that you understand kind of many things. Of course, if you just go into the extremely strong magnetic field, then you start to see that interaction-driven effect. But before then, basically, this is kind of all governed by the single particle physics. So physicists actually enjoy to study about these materials in probably now 15 years or so. But most of the single particle problems we understand in the graphene, I would say. I think there's some lingering problems, but most of single particle problem in graphene, because it's a relatively simple system, we know how to do that. But then, of course, things become sort of changes. That it's not only the 2D this graphene is not only 2D materials. Soon after this, the people start to realize there's a whole slew of the different type of 2D materials. It can be boron nitride, transition metal dihydrogenide, and even just kind of single layer of high temperature superconductor. There are many other type of the 2D materials that van der Waals layers the stacking, such that you can stack, you can peel off this material or grow this material down to monoatomic unit cell, and in principle, also you can restack them together to make the heterostructures. And also, this type of things start to give us a new interface and new the applications and new functionality one can study upon, right? So the field has been kind of evolved quite a bit ever since this first demonstration of the graphene. But nevertheless, instead of that, I'm just going to this various different type of systems, and then another exciting the physics one can explore into this diverse system. I want to actually go back to the graphene, and that discuss that something that unusual, and obviously that is related with some of this many particle physics, which has not been explored fully in graphene because it was a relatively simple system. Two important many particles, many-body quantum mechanical ground state I'm going to talk about today is related with this superfluidity and superconductivity. In some sense, in condensed matter physics, these two phenomena has been known for many years, probably almost close to the now century, and always kind of make people exciting about that. Part of the reason is inherently many-body problems, but second, actually this can be readily observed in the experiments, and then always kind of give us somewhat unusual properties, right? Such as magnetic levitations, fountain effect in the superfluid. They're full of this kind of the surprise that still we often find out kind of as a kind of amusing part of the working of this condensed matter system. They, in a sense, give us a power of this many-body quantum states, that how unusual they are actually represented under this type of system. Well, generally speaking, these are two important the many-body states, superconductivity and superfluidity, in fact, can be connecting together in common theme. Say that the superfluidity usually appears as the condensation of the bosonic particles with some residual interactions once they come into the Bose-Einstein condensation with the residual interactions, such as the helium-4. Right? Certainly the main framework that we can explain the superfluid is Bose-Einstein condensations. At the same time, that the superconductivity, the well-known theory that describes the superconductivity is that Bardeen-Cooper-Schrieffer BCS theory, that electron pairs up to make the Cooper pairs, and then that condense into this many-body states. Basically, it gives us the main framework of this the superconductivity. But obviously, the Cooper pair, that if you just ask as a composite particle, as a bosonic composite particle, you can see that there must be some connections between the superfluidity and superconductivity throughout this condensation of bosonic system, right? Indeed, that has been the case, right? In especially atomic and molecular and optics, the community, AMO community, this has been studied really extensive way, because in some sense, AMO community can come up with a system that actually demonstrate those kind of connection explicitly experimentally, right? The way is that you start with these two fermionic atoms and control their interactions by the effect of the resonance, and then you can actually control this the attractive interaction, very strongly attractive versus weakly attractive, right? And if you just have the strong attractions, of course, this two fermionic particle can forms diatom molecules, which actually is a boson. So in those kind of this strongly bounding the diatom molecules as a boson, they will condense into the Bose-Einstein condensations, right? But if you just kind of adjust the interactions and make that they only weakly interact each other, weakly attractive each other, they can form kind of particle in the momentum space like the BCS Cooper pairs type of the states. Now again, as a composite particle, this Cooper pair can condense into the Bose-Einstein condensations to form another the condensation state. Often you can call it the BCS type of condensations. Nice kind of demonstration over here is using this knot, controlling the Feshbach resonance. You can actually control the continuously that between these two different type of the many-body states in the extreme in continuous way, and hence the concept of this the BEC-BCS cross has been tested out experimentally, also theoretically. Right. Now, condensed matter physics, this type of the BEC and BCS crossover also becomes kind of quite relevant. And some people believe this, in fact, is one of these framework that one can understand the unusual superconductivity, such as high temperature superconductivity appears in cuprates. Right. Idea is in the the overdoped regime that everything's more look like this is kind of a typical fermionic system. The typical BCS type of the condensation works. However, these unusual metallic states in the lower doping site were closed to antiferromagnetic order of the with the Martin insulating gap. Basically, that might be the better description is somehow the BEC type of this description, such that prepared this forms of the prepared the Cooper pairs incoherently formed first, and that actually condensed down into the condensation in the low temperature. Whether or not this is a really kind of right framework, certainly this the many-body, two different many-body states, and try to explain that the crossover is one of the exciting themes that one can think about. Another condensed matter system, in fact, one can realize in principle those kind of crossover even more clearly, is excitons. Now we know that in semiconductor, when you shine the lights, you can create electron-hole pairs. Although this is a transient the particle, for now imagine that there's an extremely long lifetime for the excitons, and such that it can be actually think about kind of true quasi-particles in the system. Exciton as a pair of the fermionic electron and fermionic the hole there is a composite boson. Therefore, you can expect actually they can also condense down to Bose-Einstein condensations, right? However, now if you just increase this exciton density more and more, classically we know that the large exciton density means that the internal screening of these charges will make that the Coulomb interaction between the electron hole becomes weaker. So we know that classically there is a phase transitions from exciton gas to the exciton and hole, the Fermi plasma or the Fermi liquid if they are strongly kind of stay interacting, and that is what we call the Mott transitions. Right? We can ask that what happens that if you have this electron hole Fermi liquid and it's just kind of go down to low enough temperature. The recurrent expectation is still there is interactions across this Fermi surface of the electron holes strong enough that they can actually form the Cooper pair and condense down into the BCS type of the superconducting states. What you see here is therefore that a very similar way of this BEC-BCS crossover expected into the really cold atom system. In principle, controlling the exciton density, one should be able to go to the slowly from one of the many-body state, BEC type of the many-body state, to the BCS type of the many-body state. Here, the controlling parameter is basically exciton density, which determines the distance between the excitons. Right. Unfortunately, this has been only theoretical the speculation or proposal at this point. Experimental realization of this exciton condensation has been some technical challenge, contains the technical challenges. One of the technical challenges is, of course, exciton is a transient particle rather than just ground state property, which means you have to keep pumping in the exciton by the light and drive the system. So reaching this condensation with the driving system is always kind of the challenging part. So the one efforts that in this community has been made is, can we make that this exciton live long, right? One, the proposal of there is just using this quantum Hall, the double quantum well system, two parallel quantum well to each other, and each of them that you can create exciton by the shining the light. But if you bias this quantum well, you can separate the electron and holes from one well to the other wells, and the bottom of the conduction band of the one well to the top of the valence band of the other well. And if this well distance is small, then they are still strongly bound together. But now, since these wave functions are separated in the physical location, their recombinations to just recombine to bring the light back is the probability is low. Therefore, you can increase the lifetime of the exciton in such a way. This is often what is called the interlayer exciton in semiconductor heterostructures. Indeed, quite a recent experiment shows that once you have those kind of system and pumping enough excitons, there is at least people start to see that coherence start to appears in these excitonic gases, and that the spontaneous coherence appearing in this excitonic gas is very first step to just kind of really demonstrate there is many-body coherence or many-body condensation state can happen here. Nevertheless, with this progress, there has been some still challenges. This exciton is still kind of finite lifetimes object, and they're rather weakly bound. So there is still kind of more work to need to be done to improve this the exciton lifetime and bring into the really the exciton condensation states per se. However, there is yet another experimental way that one can realize this type of exciton condensations, and it has been realized again in a very similar way in semiconductor heterostructures. That's basically using the magnetic field to generate the Landau level. As we know that once you apply the magnetic field, you can create the Landau levels, and there's well quantized Landau levels, and there's a Landau gap opens up. Think about that I have again just a two quantum system applied the magnetic field, and that they actually each of this layer will form these Landau levels, and kind of Landau gap opens up, right? Imagine that for now, if I just feed up this Landau level, then of course each of the layer will just generate this quantum of physics. So we all understand quantum of physics for many years. Field Landau levels basically generate this the quantum of physics where the dissipationless edge states can carry the currents around. But if you just don't fill up the Landau level and leave the partially filled Landau level, in a sense, this you can think about bad matter. Like under the magnetic field in bad matter, it can be dissipated. Nothing too interesting thing happened with this partially filled Landau level, right? However, if I just put this two Landau level partially filled and put them very close by, then yet interesting things happen. Especially if they are filled up in complementary way, such that if I just project them as a one to kind of form the full Landau level, if I just completely project them, of course, I can fill up this whole Landau level way completely. So naturally, you expect quantum physics should be bad with this dissipationless edge state forms, right? But before you just completely collapse this two layer, just imagine that these two layers very close by, but not completely overlap, and ask what is going to happen, right? What is going to happen is, of course, there is a correlation between the electron and holes in the upper layer. Another way to say that is, whenever there is electron in the upper layers, right below the locations, I don't want to have the hole because of Coulomb interactions, or more like the exchange interaction mediated Coulomb interactions, right? And therefore, if I just think about this square mark is my just kind of one of this quantized cyclotron orbits, whenever I fill up this the square with electron, I expect to actually have there is an empty this site underneath actually behave like the hole. So if you just kind of think about how just kind of to explain this part, it's basically a bunch of the electron hole pairs just kind of floating around in this lattice, right? But as you see that, as a whole, they should form the quantum states, which means it's a completely coherent state I can build up, right? The mathematical expressions that what I just mentioned is in fact that can be just kind of expressed by the coherent connection, the combination of such electron hole pairs across the quantized cyclotron orbits, which actually kind of resembles almost exactly what you expect to see in the exciton condensations. Now, this is not the real exciton condensation in some sense. This is they generate this magnetic exciton. Nevertheless, the physics governing here is very similar to what you expect in the exciton condensations. In fact, this idea is not a new idea. It's been around already in the 90s, and also experimentally realized already in the close to 2000s. And several heroic experiments done by the Bose-Einstein and Caltech, who actually just make the double layer of the quantum hole system and make the contact on each of the layer, right? And the first demonstration is indeed in these two partially filled Landau levels, when they actually couple strongly enough by the Coulomb interactions, they behave like the full quantum hole system, such that the quantum hole effect actually appears with these partially filled Landau levels. They are as long as they completely filled. The second part they actually demonstrate is if these things happens, when you send the current in one layer and measure the Hall effect in another layer, this is what we call this drag Hall measurement. This drag Hall is Hall drag is quantized, and that quantizations can be explained again just kind of this exciton condensation idea, right? So, as I said, when this the complementary field Landau level get into the exciton condensation phase, I expect to see that the whole quantum Hall effect with the edge states. So when I send the current through this system, current should be divided into the edge states, but also in the central part, basically exciton is condensated, and then they can actually move dissipationlessly, right? So all these things can be just kind of combined together. In fact, that explains that why that we have this quantized Hall drag in this type of system, right? So seeing the quantized Hall drag experiment in this by the double layer quantum well, in fact, it's deeply related with what we expect to see that in the Exciton condensation. In some sense, this is less exciting because where it's kind of all indirect arguments. But there is actually a better way to directly demonstrate this Exciton condensation. That was, yes?
How do we ensure exact complementarity between the two fillings in the two layers?
So usually what you can do is you have the gate in the one of the layers or both of the layers.
Okay,
So you can
usually
tune this the densities. It's kind of, otherwise yet you have to carefully dope, which is kind of difficult. Right. The direct measurement actually comes in the following way. This experiment, the following way. So instead of that, you just kind of send the current to one of the layer, you can do the following experiment. You can send the current to one of the layer, but you can return that same amount of current in the bottom layer, right? So current flow here and current flow there. Now imagine that I have the excitons in somewhere, right? So this exciton, if this is the hole will flow there through these current directions, right? Current is returning here. The electron should go to the opposite directions, right? Which means that in this geometry, if this excitons are kind of there, will just kind of flow through with the current in that directions. Now note that if indeed the exciton make the superfluid, one of these most important property of the superfluid is the dissipationless the flow, right? Therefore, this is a way that you can actually expect that there is no the resistance or dissipations happen when you just make this counterflow current geometry, right? Indeed, that idea also has been demonstrated. It was Menser-Huygens and others, the other groups' work. In fact, if you just kind of make the counterflow geometry, they start to see that when this Exciton condensation happens, then basically they have the zero counterflow resistance, as if there is no resistance happen. This is rather unusual, right? Because each of the layer itself is bad matter, as I said. It's a partially filled Landau level. So if you measure each of the layers separately, it is just kind of dissipation. There's a dissipation in this layer. But once you just connect in this particular way, then somehow the system behave like this kind of dissipationless the flow where the counterflow resistance goes to zero, right? So now I'm just kind of saying that all this experiment was done, say, more than 10 years ago. 15 years ago. Why I'm just kind of bringing this up again? Well, the first thing is we can just do the experiment with the graphene, right? So we can just build up the very similar way that semiconductor heterostructures. Here they accept that this quantum wire is replaced by the graphene, and then we just insert this boron nitride, which is atomically thin insulator, so we can just put in between, and then you can get the quantum wells and do the experiments, right? Well, of course, just repeating the same thing is not exciting. Well, there's some difference is we can have the graphene atomically thin. This boron nitride separation layer can be also very thin, such that if you form these excitons, then the electron hole, they are strongly bound. So all the energy scale that we expect in this experiment is huge compared with this the gallium arsenide quantum well. Not surprisingly, we get those kind of Exciton condensation states and those kind of things. Let me skip this one. But also temperature scale of the seeing this type of experiment is now about 10 Kelvin. Exciton binding energy is much stronger. We can just do the counterflow measurements and then up to the kind of relatively higher temperature. So I think that basically first thing that we observe is a very similar physics that has been done, but higher temperature, right? Well, it doesn't necessarily teach us any more of the new physics at this point, although there's kind of some interesting things we can do with different type of Landau level can be matched, right? However, already for the experimentalist, realizing this in the higher temperature, we can do very important following experiments, right? Since our temperature is something like now 10 Kelvinish, what we can do is we can just kind of map out the phase diagram of these Exciton condensations, right? So we can just kind of do these experiments now that my zero counter flow resistance is basically my experimental the order parameter. I can just demonstrate if that is zero, I have Exciton condensation. If that is finite, I have the normal states. And simply plot that in terms of the magnetic field and the temperature, right? And this is basically phase diagram of the Exciton condensations. This blue color, especially dark blue, this is basically zero counterflow resistance. So I can call this is condensation states. Right? The reddish color is something like the 10 kilo ohms and is highly resistive in this scale. Right? That is basically the non-condensation states. What you see here is there's phase transitions between the condensation to the non-condensations. And there's interesting bowing of this phase boundary as a function of temperature and magnetic field. Right? And not only these phase diagrams, and then you can start to see that there's a somewhat different behavior in this side and that side. If I just cut it through, that constant magnetic field and just kind of look at the temperature-dependent behavior. Low magnetic field, I start to see that the transition is rather changing broadly, but high magnetic field, the transition is rather sharp, right? Low magnetic field, in fact, if you just plot it out, that how the temperature-dependent behavior, it look like the activating behavior. Basically, if you just put the RMS plots, one of the T versus the log of the R, counterflow resistance, that more or less linear and shows some of this activating energy scale. But what is important, interesting part is high temperature part is rather sharp transitions. And in fact, if I just call this is a resistance rather than counterflow resistance, it strongly look like there is a superconducting phase transitions like behavior, right? Something dramatically changing, right? And that's actually happening at high temperature. So simply this phase diagram already starts to show that this phase versus the other phase looks very different, somewhat different, right? And now you start to see that this bowing behavior of this the phase boundary is something very close to the what actually I started with when I showed the exciton condensation phase diagrams, right? Indeed, in this magnetic excitons, exciton density is controlled by the magnetic field because the distance between this exciton magnetic exciton is simply controlled by the magnetic length. That's basically what is the orbit of the quantized cyclotron orbits. So it's not surprising. By just controlling the magnetic field, I control this the exciton density, and then I can just make the crossover from this tightly bound exciton or the individual excitons that the next exciton is far away to the more of this strongly overlapped exciton where you're getting to the more close to the BCS type of the limits, right? You can actually analyze this a little bit more details, right? For example, if it is in the low magnetic field region, that so-called the BC limits, you can see that why actually we have this type of activating behavior. In fact, this BC limits of the activation gap, that once you extract the activation gap, it's actually nicely scaled with the Coulomb energies that the governing this regime, and that is more or less expected when you just write down the magnetic exciton. Simple case of the wave function I just kind of draw before. The elementary excitation of this magnetic exciton, elementary excitation is basically creating this meron and antimeron pairs with this flipping the spin structures. And there basically it has been known that this pair of the meron and antimeron, you have to pay this the energy gap, which actually is basically proportional to the Coulomb energies we observe. So this side actually is relatively easy to understand. What is actually more exciting part of this diagram is in the high magnetic field region, where you kind of get into the more BCS type of the limits. In fact, in this BCS subtype of the limits, it has not been well known that what type of the wave function I have to write down for this exciton condensation phase, magnetic exciton condensation phase. But at least experimentally we know that the transition is indeed really sharp. Not only this kind of transition look like the superconducting like the transitions, you can do the following experiments, right? Since I have the current flowing counterflow geometry, I can measure the voltage to measure the resistance. I can just do this in the nonlinear transform, sending the more currents and measure. Yes?
What is BKT? BKT, what does that mean?
BKT. I'm going to explain. That's the Brzezinski-Kostalis-Dowris transition, KT transitions. Right. Yeah. So if it is 2D phase transitions, and especially if I call this BCS like the superconducting transitions, then we can ask, okay, so 2D superconductor, what kind of phase transition we expect? Well, that has been known, right? The condensation phase in the 2D, when it's likely that especially this, all the parameters complex numbers, when you just take it out from this condensation state, you start to create this the vortex-anti-vortex pair, and that the basic transition that you expect is the costless Dowless transitions. Readily in the two-dimensional superconductor, this can be actually observed by just looking at the current and voltage characteristic. It's in the condensations. Indeed, when we actually measure that this current and voltage characteristic in the counterflow geometry, it actually more or less follows what is expected in BKT transitions. Nonlinear, the power law behavior, and this power law exponent will tell us what is the transition temperature or the vortex binding and unbinding temperature expected. And we can actually extract another this energy scale, which is basically this BKT, KT transition temperature. And we can actually plot it out, that how this KT transition temperature can be modulated by this magnetic field. And here's a relevant length scale, relevant energy scale, is just convert this magnetic field into magnetic length and compare with it the size of the exciton, in this case interlayer separation. You can start to see that this BKT transitions actually nicely just can aligns with what happens with this magnetic field directions. We don't have the full understanding why actually this type of the behavior is happening, but nevertheless, that showing that this type of the IV characteristic in counterflow geometry is a BKT transition temperatures with nice scaling, strongly suggesting that indeed this can be almost kind of smells like the BCS type of the transitions we have, right? Now this story can actually go along. You see, right? As I said, yes.
So if you go back, so I guess we wanted D to be much larger than LB, but that is half, right?
That's right. Yeah. Good eyes. All right. So I can go to the later part of the slide if you want.
No.
You're right. I think this is not in the sense that kind of deeply in the BCS limits. It's actually more close to transition limits, right? So in fact, this is bowing down. You're going to more like BC. And this is like the BCS, I think crossover regions, right? True BCS limit is really kind of crank up there.
Right.
We don't have the magnetic field to get there.
And then each
Right.
data in that
Yes.
colorful graph is one density, and then you do the thing, and then one density.
That's right. So an important part is we are staying here the new total equal 1, half field lambda. So which means that as you change the magnetic field, I have the degeneracy changes. So I have to follow that with the density. So you have to keep changing the density to stay on to this half field lambda level.
Maybe you show it. So if you apply in-plane field, I guess
Yeah.
it should also changes the circles. And all.
We don't have the in-plane field data, but that's also certainly quite interesting part, and how this all changes the in-plane field, especially when we just playing around the spins into the system. Yeah, that's another good point. Right. Okay, but as I briefly mentioned, in principle that this type of this magnetoexciton can happen in various different lambda level, right? So far that I showed you the 2 half-field lambda level in the same kind, right? So that you actually mess with kind of the edge states, right? Can also participate in the current. To avoid this edge state configuration, I have to do this counterflow geometry, right? But nice thing about the graphene, unlike this gallium arsenide, is you have the electrons and holes together, right? So you can actually put the electrons into the one electron, the lambda level, and then the other one is whole lambda level. And then in this particular case, there's no edge states, and everything should come through that the exciton condensation, and directly just kind of measure this one. So we actually did that experiment. So let me skip this one, and then half-field lambda level, and this is kind of probably a good point that I can emphasize. So this is basically new total equal 0. So across this, basically I changed this the density with the gate voltages. And across here, basically exactly I have the half-field states, and that's important point that that it's balanced, right? And if I just measure counterflow resistance geometry, which actually you can think about, it's a drag measurement, but that's okay. But the whole point here is each of the layer, again, is the bad conductors. But once you just kind of put them together, everything collapses down to 0, right? Maybe the best way that I can actually show is something like this. In this geometry, when I send the current in one of the layer, although this conductivity goes to 0, then measure the voltage across, they send the current in one of the layer and measure the return another current in close down. You start to see that whatever current I send in here, I start to kind of measure the current there. That's another way of the measuring counterflow geometry, but in a sense, this is a perfect direct current geometry. demonstrating indeed there is a strong exciton condensations happening, coupling of the exciton. So whenever I just move one of the carriers there, I tend to move the opposite side of the carrier the other directions, where the current flow is kind of opposite directions, right? So in this particular case, we can actually prove this one without messing around, that even the edge states that appears in the typical quantum or the bilayer. Right. So at this point, I can say that this is kind of rather exciting system. By just combining these two graphene layers together and applying the magnetic field, one can create this the magnetoexciton states, and they can be condensated. Depends on the choice of the different type of the Landau level. You can actually create a different type of flavor of this exciton condensation. I think that's kind of another interesting part. Also, we can just kind of make the phase diagram. This type of the experiment actually can go in kind of many different directions. First of all, that you don't have to even just use a graphene. You can use semiconductor, and you can just follow through the very similar way of what has been done in the semiconductor heterostructures. Again, using the light, you can create the excitons, but difference in the two-dimensional system is exciton can be strongly bound because their separation is small, such that you have the larger energy scale, and that they have the longer lifetime, and all of these things allows us to actually bring these real excitons without magnetic field, also make condensed. So that's kind of one of the directions. Another direction is even for the graphene. Now you can just apply even stronger magnetic field and a better quality sample and ask what is going to happen. Well, what is going to happen is I just mentioned that half-field lambda ray is going, but that's not true, especially when you get into this very strong magnetic field. Half-field lambda level actually produce more correlated state, such as composite fermions, and that fractional quantum effect associated with it. Now you can have the composite fermions. Again, you can think about whether this composite fermion can couple together, form this composite fermion excitons, and what type of condensation state to look like. We start to already have that evidence that indeed you can form this composite fermion excitons, and they actually behave quite different way of the conventional exciton condensations we have. So all of this direction is actually, again, the directions opens up that going for the next level of the studies, right? But as I said, my talk has two components, and I just can finish one component of superfluid part, right? Already you got the sense that although this is superfluid, in particular geometry such as quantum flow geometry, that you may actually get the sense of the superconductivities connected in these problems throughout this BEC-BCS type of the crossover issues. Yes, question?
In the BEC regime, do you have a handle on the exciton-exciton interaction?
So exciton-exciton interaction is handled by the magnetic field, right? Basically, that's controlling the distance of the part. Other than that, basically, they have the dipolar interactions they have. In principle, if you just use change the dielectric environments, you can also tune that these interactions.
So you can interpolate between weak and strong?
That's right, yeah. At this point, this dome that we have, that especially pinnacle of the dome is where that really crossover is happening between the BEC limits and the BCS limits. That's our understanding. Yes?
Kind of along the same idea as the composite fermion picture. If I think of it like when you have the half-field level, you have an exciton. Now, if I go a little bit away in field from the half-field level, is there a way of thinking of it where that's actually like applying a small magnetic field to the exciton superconductor if you're in the right regime?
That's right.
You do those kind of things and kind of kill it.
Yes.
And does it die the right way for? Because BKT would be different than
That's right.
BCS.
Yeah. And it's actually even more weird in some sense because the composite fermions, their charge doesn't necessarily be the same, although they can couple, right? So it is, you can think about this as excitons, but charged excitons, right? As a total, there is some charges and so on, right? So I think this is kind of rather exciting period. This can keep going on. But I want to actually move on to the slightly kind of different topic, but related, right? Well, I know that last week that you had this colloquium talk in the same place here, that Pablo Arriola at MIT came and gave a probably beautiful talk. I heard it multiple times. The big news arrived in the last year in the APS meeting is basically graphene becomes a superconductor. And that was kind of completely unexpected, right? Part of the reason is graphene is a rather simple system. And as I said, well, that there are not many electrons in graphene. If you just compute the spatial density of state near this neutrality where the most of action is happening, it has a very small density of state. In fact, the density of state in single particle picture vanishes right at their point, right? So if you just think about simple BCS type of the story, well, basically small density of state does not promote the interactions there, such as superconductors or multi-insulators, and those kind of things probably out of pictures. And graphene, therefore, is probably good to understand some of the single particle pictures, but I don't expect to see that something like the superconductivity and magnetism readily appears in the graphene unless you just do something very different, right? What the Pavlos group actually showed out of their few years of the work is, well, things can be different, especially when you stack this graphene together, such that these Moiré patterns can engineer graphene band structures. In particular case, you can engineer band structures such that you can create a very, very narrow band. And of course, this narrow band, at the middle of narrow band, you promote this the large density of state, which can actually create some of the correlation effect, right? So their first paper actually demonstrated, indeed, if you just kind of tune this angle between this twisted graphene layer well, and then you create this so-called correlated insulator. Often some people call it the multi-insulator, right? So it was the middle of the band, but because it's so narrow band, the gap opens up by interactions and correlate states. And what surprise comes afterward is basically if you dope this correlated insulator, like the kind of analogy of the cuprates, it becomes a superconducting, right? Well, superconducting transition temperature is reasonable, say about Kelvin or so. It's not too high, but nevertheless, surprise and exciting part is somehow there might be some interesting connections that one can make with another important problem, such as a cuprate, just kind of looking at this correlated insulator, doping create the superconductor. There's kind of some exciting connections one can make. Ever since this discovery, then many theorists as well as experimenters start to work on similar system and try to realize these correlated insulating states or correlated states out of rather simple system like the graphene. What I'm going to tell you today is basically indeed we see somewhat similar but also somewhat different type of the correlated states out of the graphene, and that's basically second part of my talk related with this ferromagnetism and superconductivity in the system. And you start to see that this title is a little bit weird, the ferromagnetism and superconductivity. They usually don't go well with each other, right? And there's a reason for that because, well, ferromagnetisms tend to break this time reversal symmetry spontaneously by kind of giving some the directions of the magnetizations. Superconductivity requires this time reversal symmetry, so they don't go really well often, right? But not always. There are some examples that the ferromagnetic superconductor do exist. And usually that is a strong, the heavy fermion system. And the first kind of clear demonstration is this uranium-germanium-2, where that you clearly see that there's magnetization appears that below something like 50 Kelvin, superconductivity appears something like that a few Kelvin-ish temperatures. Therefore, that you can see that there is a coexistence of the magnetizations, magnetisms, ferromagnetism, and the superconductivity. In fact, this was done under the pressure, and by controlling pressure, you can kill both the superconductivity and ferromagnetism at the same pressure. And this is strongly indicating that there might be some interesting tie with this ferromagnetism and the superconductivity. After this, actually, that community found that a few other of these the compounds, mostly the uranium contained the heavy fermion system, and some of them becomes even superconducting and ferromagnetism without pressure, ambient pressure, right? But common thing that you find in this example is that usually when you look at this phase diagram of superconductivities, especially when magnetic field is applied the hard axis of this magnetic moments, your phase diagram, superconducting phase diagram versus magnetic field and the temperature is rather unusual, right? There are sometimes this re-entrance of the superconductivity appears. Often this phase boundary is non-monotonic, and there are some signatures that somehow the spin texture that what make this superconductivity actually is rather different from conventional superconductor we know from the BCS. And often that this is one of the exciting part. Maybe this is the first way getting to the so-called topological superconductivity, which actually is based on P wave or P plus IP type of this, the pairing symmetry, right? Although, as far as I know, that this field is yet kind of debating whether this is a really unconventional the topological superconductivity, but there are some ingredients out there. Perhaps the most clear cut, everybody agrees that this is a topological superconductor, is probably superconductor helium-3, A phase. We know that helium-3 is fermions, and when you just kind of cool down enough temperature, they actually form the Cooper pairs and condensated into this superconducting condensations, right? However, in this particular case, they interact because it's neutral. They interact with the very short-range interactions, and to mediate this the pairing of with the short-range interaction, it turns out this superconducting helium-3 to utilize a p-wave pairing as this pairing mechanism, which means there is the tendency that the spin can be aligned in the same directions. It can be spin triplets, right? And especially in this, the A phase of the superfluid helium-3 shows that this A phase and kind of quite intriguing, the transitions under the magnetic field. When you apply the magnetic field into this superconducting helium-3, you immediately see that there's a two transition appears, and one transition actually goes to higher temperature, and the other transition goes to lower temperature. An interpretation of those kind of the behavior is indeed that this is a Cooper pair made with the same spin, right? Either spin aligned with the magnetic field, spin anti-aligned with the magnetic field. Because of Zeeman effect, one of this Fermi surface becomes large and the other one is small, and size of Fermi surface is of course tied with the density of state. Therefore, that's simply that using the idea of the BCS type of the idea, we know that the transition temperature goes up and down, depends on the direction of the spins aligned, right? So, but important part is that this is the way that you can create this Cooper pair with the same spin, and this will becomes kind of the topological superconductivities, right? So I think this is kind of one of the interesting part, and especially related with this realization of topological superconductivity, which is now one of the excitement of this quantum information process, because this is one step going toward this creating the topologically protected superconducting qubits out of it, right? Can we actually get the really the material platform to realize this one? And this is something that many people, including Jogare, is working on to try to realize material platform. Right. So another ingredient I need to introduce at this point is Mott insulator, because that is a kind of correlated insulator that we pour in the graphene, and let's kind of briefly just kind of review that. Mott insulator itself is that basically you have the band insulator when you have the completed field of the band, but of course partially filled band is the conductor. But once you just draw the interactions between the electrons, especially strong on-site interactions there, that due to this Coulomb interaction, you can block this motion of the electron from one side to another, and that effectively just open up the gap into the single particle band structures, and that proportional to the size of gap is proportional to on-site Coulomb energies, and that's kind of simple view that you can create this Mott insulators, right? Of course, this this Mott picture at this point itself does not tell us that what is a spin happens onto all these sides. Now, of course, if you just throw this, what is the residual exchange interaction between the electron in the sides, depends on this exchange energy scale, the structures, you can make the spin structures, right? Often that Mott insulator in the scale with the short range of the interactions, that spin tend to anti-align, such that most of the Mott insulator we know is antiferromagnetic Mott insulator, right? But nevertheless, Mott physics itself does not completely dictate what is expected magnetism there. In fact, if you somehow make these interactions between the residual, the electrons in the Mott the lattice is relatively long range, one can actually make this ferromagnetic the Mott insulator. Indeed, experimentally, it has been seen that ferromagnetic Mott insulator do exist. Here is kind of some of these examples here, right? It was done by the Ian Fisher's group recently. And there are a few examples that are not as common as antiferromagnets, but ferromagnetic Mott insulator kind of exist, right? Now, coming back to the Mott insulator, the realizing graphene in the Pablo's group. Well, again, that at the so-called graphene magic angle, that you can get this flat band, and that you get these gaps, and that make the superconductor. How about the magnetism? What they see in this experiment is apply the in-plane magnetic field only coupled with the spin. they start to see that the Mott gap actually shrink down and disappear and strong enough magnetic field. And the idea is basically that means that two Mott insulator, basically it is the spin degenerated or spin up down, and applying this in-plane magnetic field, due to the Zeeman effect, they will just kind of close down this Mott gap such that you're just coming out from the insulator, right? Whether this is antiferromagnetic or this is spin unpolarized, this is kind of some of the debates, but we know that there is no kind of strong magnetic structures that we can find out in this type of things. So here comes that kind of the last pitch of my talk, right? So what we did is we just repeat very similar experiment to different system. The next simpler system is so-called the graphene bilayer. So each of the graphene layer is Bonner stack, and you just put this two Bonner stack layer with this some small twisting angle, right? And just kind of have these 4 graphene layers and just do the very similar experiment. In fact, there is a motivations why we are doing this one. That was actually the idea of one of my graduate students, Xiaoming Liu's idea. Well, when he was kind of proposed this idea is following. Right? Well, to have this the graphene single layer in this strongly correlated multi-insulator superconductor, you have to tune this angle really, really right. And Pablo explained that in the last week. Probably the physics is basically, well, when you stack them together, there is a residual layer interactions will deform your band, and this deformation is such a case that more or less match with the separation of this band, and there's kind of the main ingredient flat band formations, right? And that really requires sharp tuning of the angle, so-called the magic angle within the accuracy of 0.1 degree or something like this. However, in the bilayer, you can apply the very similar stories, and you can come up with, all right, so you need a kind of fine tuning of the angle. But there is an additional knob that we have in bilayer. In Bonner stack bilayer, basically that there's inversion, there's inversion symmetry in this lattice. However, applying the electric field, you can break those inversion symmetry, and then the band gap is deformed, and then actually tune this deformation of band with the electric field that you applied in vertical directions. This can be done simply just putting this top and bottom the gates in there, right? What is the advantage we have? This one, in principle, you don't need to really sharply tune the magic angle, because any angle, the descent angle, you can actually do the final tuning by apply the electric field in the vertical directions. So that was the motivation we started out. Of course, you have to go through a little bit of more detailed calculations. What is angle ranges? We have the great support from the Ashwin's group in-house, and they just give us the what is the range of this angle that you expect, and what is the displacement field. You just get to this flat and isolate band, which is basically the basic ingredient that we expect to see that this strongly correlated gap opening in the single particle band. So based on this this math, we just choose, all right, so let's go for something like that, somewhere there, say 1.3 degrees, and we can tune this displacement field and ask that what is going to happen. So this is kind of data. So this is device schemes that we have this top and bottom gates, which actually control that by the gate voltages, right? So along this diagonal line, basically we just change the density, filling of the band along this diagonal. Then we actually have the different polarity, which can tune the electric field. Along this line, that basically we tune this density along this line. We have the different polarity such that we can just change the displacement field. So this is charging neutrality, center of the gap, and this is part that we expect that so-called the single particle gap opens up, right? So at the corner of the left jaw. Usually correlated state appears somewhere at this half filling or some of the in between, right? And what you see here is that there's nothing there, but in this side, when I just have some displacement field, electric field, I start to see that there's this dark red region, which is kind of insulating region that appears in here, right? So certainly there's a correlated insulated state appears in the half field band, right? But that only appears with some finite displacement field. So that actually that going well with these pictures that we initially started with. Indeed, that if we just measure the correlated insulating state there, as we increase the temperature, it disappears from there, that we can get the activation energy. Something like a few millielectric volt of this decent size of gap appears and stabilized by the displacement field. Right. And applying the magnetic field and look at all this quantum oscillation, we get this mass, and that all of this state we are just creating there as a reasonably high mass, which also kind of supporting that this is really the correlated states with a reasonably high mass than single particle gap. Right. What is interesting part is applying the magnetic field in the system. So when we just do this one, we start to apply the magnetic field, and we apply the magnetic field in the following way, right? So we just kind of choose one of these correlated states and apply the magnetic field and ask what is going to happen, and especially we apply the in-plane magnetic field. Do not touch with any orbital structures in principle, and just kind of look at the spins. And this is a way that you can get this, whether the spin is aligned or anti-aligned, and that pictures. What you see in here is when you apply the in-plane magnetic field and increase the magnetic field, let's kind of trace that this half field lambda level. And in fact, actually, that becomes much larger than what we started with. So indicating that it has becomes stronger. And more exciting part is even just quarter field states, which was not missing in the zero magnetic field, start to appear. So therefore, that there's some spin structures can be reinforced under the magnetic field, in plane magnetic field. You can do a little bit better job just looking at all the temperature dependence and kind of plotted out the gap. It turns out gap is increasing with the in-plane magnetic field. That is a completely opposite case, what has been single layer. And naive interpretation we can throw that here is indeed this is indicating probably each of this the correlate states or the mod states is spin polarized, such that when you increase magnetic field, that simply Zeeman splitting will just increase the gap. Indeed, the indication is the slope here that we measured is more or less tied with this Zeeman gap increase. So we know at least that this strongly suggests kind of spin polarized mod states, right, or ferromagnets, if you want to say, right. We actually just choose different angles. Now, especially go to the very small angle, so that going to the bit slightly different Chern numbers. And then what we see that is indeed kind of similar things happen. Applying the magnetic field, that we start to get this displacement field. We start stabilize this correlated insulating state with the finite displacement field, as we have. But here the huge difference here is when you have this doping on this correlated insulating state, actually we got also superconductivity, right? And this superconductivity is rather robust. And again, you can just measure the transition temperature is something like the 6 Kelvin, or a little bit better way, quantitative way, is a rather 50%. You can measure the KT transitions IV curve, and from there you can extract this again KT transition temperature. That will give you about something like the 3 Kelvin order. So I know that there is a kind of rather robust conductivity appears here. And this superconductivity, like this, the gap can be controlled by both the electric field and magnetic field, right? So you can have the tunable superconductivity in that way. Okay, so that part is not surprising. When you apply the magnetic field, you of course kill the superconductivity. And once you kill the superconductivity, all sort of this quantum oscillations happening from this all the kind of band structures, right? That itself is not surprising. But once we actually see this data, we already start to see that something is kind of somewhat strange. The phase diagram of this the magnetic field the temperature is slightly different from that what we normally see in the mean field already, right? Especially this one is actually taking apart a bit kind of steep. Of course, vertical magnetic field is not a good way. You can just interrogate the spin structures. Again, this because coupled with the orbital. So the strongest evidence is what if that you apply the in-plane magnetic field in the system? Ask that how the superconductivity changes. Right. So like before, on the similar case, we apply now in-plane magnetic field and see that this is the correlated gap and dope that we get the superconductivity, and we ask that how that changes. In-plane magnetic field also killed the superconductivity, but how it got killed? If we just kind of look at carefully that at the constant the density and plot it out the phase diagram versus B versus T, you start to see that phase diagram is very different, right? If I just chase 50% of the transition temperature, it will look like this. If you just do a little more quantitative job, just make the BK transition temperature, also kind of shows like this, right? what is the important part is that very low magnetic field, where that you start to see that superconductivity actually enhanced with applied magnetic field. Right? In plane magnetic field somehow increase the TC. And that is a very strange statement we can make. Right? Usually magnetic field always tend to kill. So what is really happening here? What is really happening here is basically we believe that tied with the spin polarized the correlate gap, this actually indicating probably the Cooper pairs made out of the same spins in the system, right? So our collaborator, Ashwin's group, actually come up with a kind of simplest arguments. Again, like the superfluid helium-3 case, if you just think about there's minor spin and majority spins that they constitute the ferromagnetic, the Mott gaps, right? If you just kind of dope this system to create the superconductivity, basically you have the two pieces of the Fermi surface with polarizations. And like the helium-3 case, when you apply the in-plane magnetic field coupled with the Zeeman field of the spin, you actually tend to increase that TC in one of this Fermi surface, will actually tend to increase the TCs in the system. And strong indication is then you expect this linear increase of the TC with the magnetic field, and the slope is kind of more or less should fit with the Zeeman energy. Indeed, just we confirm that if I just fit this linear curve, that is more like the Zeeman energy we expect to see, and strongly indicating this might be just kind of at this point indirect, but suggestive the case that making this spin polarized superconductivities in this system. All right, I think at this point it is just kind of the status report. I think all of this, the two paper I just tell you today is in fact even just written up yet, but we are fairly confident that this result actually stays quite strongly and indicating that both actually shows quite intriguing directions that we can push onto the realizing this many-body state into this relatively simple graphene story. Of course, this story goes on. You don't have to work on the graphene, right? I think that there are many other two-dimensional systems. You just stack these materials. For example, here the two semiconductor, the tungsten diselenide, right? Stack them together, and you can create this correlated insulator states. And not surprisingly, when you just dope this one, it also seems like they're showing that indication of superconductivity is there, although this data is less solid than before. But at least this kind of tells you that there are kind of fertile playground that we have. Just kind of using these 2D materials and their different stacking, we can actually study about the strongly correlated system at this point. Thank you very much. I actually thought this most important this slide, and especially important slide that is this guy, the Xiaoming Liu I just briefly mentioned, and all other collaborators are kind of important. But Xiaoming Liu is indeed the amazing graduate student just finished up, and he's actually did both of the experiments that I showed you today, and then I should say that he should get all the credits that I present today. Thank you. Any question from the audience? Yes.
So in the bilayer Landau level experiments, you
Yeah.
really have independent charge conservation in each layer, and the coupling is really drag and electrostatics only, right?
That's right.
So
Yeah.
that makes for the real symmetry of what you would like to have.
That's right. That's right. So in principle, we can have the one Landau level is very different from the other Landau level, and we can still kind of coupled by the Coulomb interactions, right? So that's in a sense a kind of big technical advantage we have on the graphene compared with the quantum or bilayer. And due to the limitation of the growing gallium arsenide heterostructure, any semiconductor heterostructures, you don't have a lot of tunability in that system. But in graphene, basically, we have a rather strong kind of wide tunability. You can couple any Landau levels that you want.
And one question about this bilayer and bilayer. So I guess you have a spin and valley and a layer degree of freedom.
That's right.
So if you go with that argument, you want to be at ns divided by 3.
Yes, okay. No, actually, ns divided by 8 is probably things. But what required here is basically there is a strong, it's reasonably strong with the interactions, and that's how that you got deformational band, right?
Okay.
So basically, you remove this the layer degeneracy because that layer, I think, were coupled. Symmetrical coupled and anti-symmetric coupled actually kind of bring the energies different. So we are focusing on the lowest energy state. So layer degeneracy is removed in that way. And then we still have the spin degeneracy and valley degeneracy remain. And that's why that's a factor of 4 comes in.
I have another So in the last part of your talk,
Yeah.
you showed m star over the electronic mass.
That's right.
Right?
Yeah.
And you talked about mass enhancement.
Yeah.
So to document that, one has to compare to the band mass, I suppose.
That's right.
What kind of values do you get?
Right, so we have about 0.3 compared with the bare electron mass. So let me see whether I can find it right. No, I think it's the other way around. Yeah. So we have about 0.3-ish,
Yeah.
0.2 to 3-ish.
Uh-huh.
So it's not have fermions, but the bare mass, band mass here is about 6% of the 3 to 6% of electron mass. But it's about 10 times enhanced.
Okay, so
compared with,
it's a fairly big.
yeah, it's a
enhancement.
fairly big. Yeah, it's about 10 times more
Okay.
than just bare electron mass
Factor
in
of
simple
10.
band structures.
Any other questions?
Yeah.
So this is a quite ignorant question, but graphene has a sublattice structure, so it has more quantum numbers, which are reflected in details of the Landau
Yes,
level.
right.
So the question is, does that translate into interesting structure in the excitons?
A priori, indeed, it is magnetic-excitons, and no, because I think it's simply the Coulomb interaction, so there is no exchange that I need to consider.
Oh, but there is
yeah.
another, my question is just, is there another quantum number floating around? And
That's
then
right,
we can argue
yeah,
about
that's
how
right.
to couple to it.
So indeed, there is additional quantum numbers I can just in principle couple to it. Unfortunately, that is not encoded in the exchange interactions
Okay.
between this one. But nevertheless, because of this one, that when you have this the excitons, that you can have the excitons with the different internal quantum numbers.
Yeah.
You can just play around. Indeed, some of the, not the single layer to single layer, that in bilayer to bilayer, it's a bit complicated excitons. There, the additional quantum numbers that plays some roles because that will change the wave functions that will govern this the Coulomb interactions there. So there's some result that we had together with Correlated showing that indeed that is additional quantum number you can play around and get some different transition temperatures.
Great.
Yeah.
So in twisted double bilayer with the superconductor,
Yeah.
so yeah, like you said, you apply magnetic field and it looks like it increases the TC a little, which is saying
Yeah.
something about spins being important, so it's somehow p-type-ish. My question is,
Yeah.
is it just p-type or is it necessary?
No, I think that's still kind of need to be considered because.
Because what would be breaking the other symmetry? Why are
That's right.
spin
So
momentum
I think
not
that
both
likely
good?
what happened is it is a equal spin pairing,
Yeah.
but it's probably likely the Valley singlets. Right.
Oh, okay.
So,
No.
but when you just write the Valley singlets, whether there is a kind of whether this is P type or P plus IP or there's even S type, there's many different possibilities. So I think that at this point I cannot say anything about this pairing symmetry, but at least we have the first step.
Oh, yeah,
Right,
yeah.
so equal spin pairing, I think that's kind of first step. Because if the spin singlet, then basically that's it, more or less, right? So I think there's a first step, and next step is whether what is really pairing symmetry. That actually requires more of the experiments. So potentially that you need kind of phase-sensitive experiments to prove that. But at least we are hopeful that at least we have the first steps passing through.
I'll ask one more question
Yeah.
and maybe we can end it. So I guess you can just imagine I have 3 layers and then I have another 3 layers and I will do this.
Yeah.
Is there any advantage to that?
Yes, I think of course after Pavlov's experiment, many people just think about very crazy things, right? I thought that this is already crazy enough, but then the next level is what if then we have the 3 layer, like twisted this one, but twisted back is another one, or even more twisting. So I think there are kind of many different proposals, especially tri-layers with the middle layer twisted. I think that could be some of the things you can even tunables, even flatter band may appear. You don't have to even go for this twisting, even just the ABC tri-layer. I think there's a report that you also get a very flat band, and somewhat similar physics has been seen as insulating states and superconducting states appears after insulating states. So these are rather kind of common that by just kind of various different engineering this the stacking, there is a possibility you can engineer band structures, and whenever this band promote a really flat band, large density of state, seemingly that is a kind of good place that just hosting the correlated states.
So more to come, I guess.
Yes, I hope.
Okay, let's thank Philip again.
Yeah. Thank you.